All right, now let's get to start writing on our project that utilizes the shared memory as a buffer for each block to perform the calculations that's needed, and then copy the values into the global memory. Now, later in this project, I'll also show you how you can utilize CUDA events to be able to calculate the speed of your operation in calculation. However, since our processes that we're doing here in this case are fairly simple, we will not really see any differences if we just use shared memory or not at all in terms of accessing the global memory. But if we do use programs, for example, the project 2 that you're going to be writing in terms of calculating the blurred image, there's a lot of processes that are happening within each kernel, which makes the shared buffered memory a very, very useful time saver in terms of performing our calculations. So with that, let's start implementing our program and writing. I'm just going to go ahead and real quick show you the different parts of the program before we delve into writing the program. So first off, I created, if you skipped the video lab part 1, where I set up this project. So basically I'm using OpenCV and CUDA side by side. I created a dimension and I used 512 pixels for the width and height of my image. I also created a constant k equals 16. That would be the size of my block. And pi 3.141592 is basically the pi number. I created a helper function, and I call it GPU calc image, and I'm passing to that a matrix reference, which is going to be the image that I'm creating. My kernel is called GPU-W shared memory, and it passes as an argument a pointer to the global memory. I'm calling this pointer destination. In the main function, I'm creating my GPU image. It's of the size 512 by 512, and it has RGB, unsigned integers, and I'm going to basically call my helper function here to create it. And this is my helper function, GPU calc image, and it's passing a matrix. So to use that, I'm going to call my helper function, so GPU calc image, and I will pass to this my GPU image to my helper function. Now I need to basically write out my helper function. Remember, the helper functions that we are using are fairly straightforward. We're passing the data from the host in the form of the reference image here. Then I'm creating a device pointer. So now that I have a device pointer, I need to perform the 4 steps that we talked about. And it was actually a question on your midterm exam that you need to create and allocate memory on the device. Then if you need to copy data from host to device, you have to do that. Then you invoke your kernel to perform the calculations. And finally, you basically perform a CUDA memcopy from the device back to the host so that you can use the result of your program. So first things first. First off, I'm setting my device. I have only one GPU here, so I'm setting GPU 0. And the next step, I'm going to perform my CUDA allocations for the memory. So my error CUDA status that is created as a CUDA error underscore t to catch the errors, I'm going to use that. So it's going to be CUDA status equals CUDA malloc. Now, as a part of CUDA malloc, I need to pass in the reference to my device pointer. So it's going to be a void pointer reference to device underscore pointer. And the size of this pointer that I want to create. Remember, I created an RGB image, so I need 3 bytes. And then the size would be my image dot rows times image dot columns. Essentially what I'm creating is I'm creating my device pointer, allocating it on GPU, in the GPU DDR5 RAM, of the size equal to the number of rows of my image times number of columns of my image times 3 bytes, one for R, one for G, one for B. Where did I get the 3? Remember when I created my image, I created each pixel as a CV8UC3. 8 is 8-bit, UC is unsigned character, 3 is the number of those bytes. So I have 8-bit bytes that are treated as unsigned characters, and I have 3 of them per pixel. Therefore, I need to have 3 times this number of rows in my image times the number of columns in my image. Then I'm going to test to see if the allocation failed. If the allocation failed, CUDA success will not be equal to CUDA status, or CUDA status will not be success, and I basically print out that CUDA malloc failed and I go to the error. Now that I have created my my kernel, I need to, or rather my allocated my memory, now I need to create a grid of blocks, and each block I need to create the dimensions for the threads. So I'm going to use the dim3 function to create a grid that is going to be the size of dimension over number of threads, comma, dimension over number of threads. And then with this argument, I'm going to create block, and each block will be the size k by k. Okay, so basically here's, let me just switch over to my board here to show you what I did here. So if this were to be my image, so if my image is the size dim by dim, and remember I said dim is 512, so if this were to be my image, okay, what I created actually effectively is I created a bunch of blocks, and I made each block to be 16 by 16 threads, right? So when I created these blocks basically I use number k for how many threads I want in each block. So this will effectively make a bunch of blocks, right? And remember, each of these blocks is effectively 16 by 16 threads. So that's why I did a dim3 block. This is basically effectively my block size of k comma k. So this will create a block size, each block size of k by k blocks. Now remember I said the dim is the size of my image, right? So the dim is width and height of my image. Now how many of these blocks would I have? Effectively I would have essentially dim divided by k in both of these directions. That would be how many blocks I would have. So if we go back to our code, what I created, essentially I created blocks of size k by k, and that makes my grid size to be dim over k comma dim over k. And when I have these blocks and the grid created, basically blocks and threads created, now next step is to invoke my GPU, and that would be essentially also very easy. So I'm gonna have I think I called my block GPU with shared memory. How many? The grid size, comma, block size, and the pointer that my code will use is called device pointer. So effectively what happens is I'm going to invoke my GPU with shared memory, which in my case is basically an empty shell right now, that takes a device pointer. So if you look up here, I'm going to have an unsigned char pointer that goes into this kernel. And then I'm invoking these many threads, block, comma, or rather grid, comma, block. Now again, remember, grid is the grid size, how many blocks in X and Y, and then block here is block size, how many threads in X and Y inside of the block. Um, Now, once my kernel has been invoked and it calculates whatever it needs to do, I'm going to perform another catching of the errors. And if the CUDA status is not CUDA success, that means that my kernel did not work or did not get invoked. And from there, I'm going to show out the error. Now, finally, when my program actually executes and it computes, then what I'm going to have to do is to go ahead and copy my data from the GPU into my CPU. So I'm going to use again CUDA status equals CUDA memcopy. Actually, I'm going to put this CUDA memcopy later on after I synchronize my device. So when I synchronize my device, yeah, let's go down and perform our CUDA memcopy here. So CUDA status is equal to CUDA memcopy, and I'm going to copy the results from my device to my host. So it would be my image data. That would be the destination. The source will be my device underscore pointer. The size will be 3 times image.rows times image.columns. And the direction would be CUDA memcopy device to host. And then again perform another test to see if CUDA status is not equal to CUDA success. Then we will print on the screen that CUDA memcopy failed. And then jump to error. An error is basically a label. Now, if it failed, we exit over every other part of this program and go to the end of our function to return the error back to the main function. So, so basically, this is my entire helper function. Again, I'm going to go over the basics of it. I created an unsigned char device pointer, which actually I had. Then I reset my device. I allocate the pointer on the GPU. I create the grid and block sizes. Then I invoke my kernel. When it's done, I synchronize my device and copy the data from the device to the host, and that would be all that I need to do with my program here. So let's compile this and see if we get any errors. I have an error. Let's see what that error is. Okay, I found what my error was. GPU with shared memory is my kernel, and it's a void kernel. I mistakenly made it equal to CUDA status. It doesn't have any return type. That was the error. So when you invoke the kernel here, remember you invoke the kernel just as a void kernel because it doesn't return anything. Okay, so so this is a code that compiles, and it should have no problem with it whatsoever. If you perform the calculation, you're going to get an empty image because when you call the kernel, when you allocate the device, the data from the kernel, it's going to be just garbage in it. And so it's this is expected that you get the results. The reason, again, if I call my program and run my program, it's going to go to GPU with shared memory, and as you see here, nothing happens in my GPU program, and that's why I'm getting this kind of random image from my GPU. So the next step of this process is for me to go ahead and create effectively my program. Okay, so the program that I would like to do, I would like to write. It basically, I'd like for it to do this operation. To take each pixel. So let's suppose that I'm going to go and I'm going to look at this pixel. What I would like to do is to basically look at its pixel location in terms of its location in X and Y dimension of my image. And then from this to create a value. And what I would like this value to be, I would like it to be basically the result of a sine function calculation. What I would like it to be is to be 255 times sine of this x, basically with some frequency. Let's call it f of x, plus 1 times sine of the same frequency on the y location, plus 1 divided by 4.0. So what I would like to do is to have this pixel created and then look at its location in x and y and see what would be if this pixel belonged to a circle. What would be the value of that pixel if this circle was centered in the center of my image? So so this function is basically performing that operation. It sounds like a random calculation at this point because it kind of is. But this is I'm using this equation to basically demonstrate the shared memory and buffering of the shared memory in your programs, and what would be the benefit of it, and what would be the pitfalls that you would like to avoid. Now, the idea in this case then is you could basically directly read or write from the global memory. But as we said, the read and write from the global memory is going to be an expensive process. Furthermore, although this is just a simple one-pass equation, you may actually have a for loop that requires to calculate this equation over a number of times, which means that every time if you wanted this f of x and f of y to come from the global memory, every single time you would have a global memory access, and that would be a bad thing in terms of speed. Now, my idea is now that I have a block of for my image, a block of dimension k by k, what I can do is I can create a shared memory for each block that I would pull out the content of the global memory once, or I write into the content of the global memory once. And then I perform these intermediate calculations that I need to do instead of over the global memory. I perform this calculation on my shared memory. So then the idea is that if this were to be my image, then what I would do for each of these blocks, I'm going to calculate a shared memory that would be of the same size as threads in the block. Then I would have each thread associated with one of these pixels in the shared memory, and then I'll have them perform whatever they need to do on their corresponding shared memory location. And when they're done, I'm going to have them then write back into the global memory for this block. So this would be the block for this image. So if you look at, for example, for this block at the bottom here, I'm going to perform the same thing. I'm going to create a block of shared memory, and then what I'll do is I'll pull the data in once, and then I have each of these threads work on their associated pixel in the shared memory. When they're done, then I'm going to have them write the results back into the global memory. So this is what really saves us and saves speed, especially if you have a bunch of processes that need to be performed on these pixels. You don't have to keep going back and forth between global memory and your threads. You essentially pull the data in, cache it in your shared memory, perform your operations on it, and then store them back into the global memory. This is what we're going to do. Now, there's a very interesting concept here that we need to be a little bit aware of. And I'm going to perform this calculation for you so that you would see what is happening when you actually associate a two-dimensional block of two-dimensional threads with your images. So in this case, what I have is I have an image of size dim by dim. And then I break this into a number of blocks. So let me use a different color for blocks. So I'm going to break this image into a number of blocks. And then what I'm going to do is that for each of these blocks, I'm going to have a number of threads to run. Okay. So now let's suppose that each thread is associated with one pixel. Okay. So then what I'm going to have is I'm going to have for the threads, I'm going to have a thread index .x and .y. For each block, I'm going to have, let's write it in black. For each block, we're going to have a block index .x and block index .y. Then each block will have a block dimension .x and .y. So this is block dimension .x, .y, and this is block dimension .x. Now, when you look at this, what would be this pixel's location? Let's write it in blue. So if I look at, for example, this thread, this pixel, and I'm wondering what is its actual x and y, and how can I calculate this actual x and y with respect to its block number and its thread number. I know that this pixel basically has these values associated with it. It will have a thread index .x and a thread index .y. Also, it will have a block index .x and block index .y. Okay, so because this is thread index.x comma thread index.x .y of block index.x block index.y. So for example, in my case, in this case here, this would be thread number 0 comma 0 of block number 1 comma 1. Okay, so how can I calculate the actual x location off of these numbers? And remember, since I have each block basically will have a block dimension .x and a block dimension, let's call this bdim .x and bdim .y. That's how many threads in x it has and how many threads in y this guy has, right? So the fun part about this is that the calculation is actually rather simple. The x location, actual x location of this thread, what its actual physical x location is going to be calculated with this equation. It's going to be thread index .x plus block index .x times block dimension .x. Let's take a look at it and see how it works. If the pixel, the thread belongs to the block number 0, then its thread index is going to be equal to its x, right? In block number 0, the thread index is going to be 0, 1, 2, 3, 4, 5, all the way to whatever maximum number of threads it is, right? So the x for the block 0 is going to be equal to, so for block 0, the x is going to be equal to the thread number. So this is for block number 0. So the thread index is going to be equal to the x itself. Now, if you go to block number 1, then the thread index starts from 0 then, right? So in block number 1, thread index will be 0. So for block number 1, the thread index will reset to 0. So then the block index will be 1, and there will be, say, 16 threads inside of it, inside of each block, right? So then the thread index for block number 1, it starts from thread index that resets, plus how many threads are before it. So how many threads are before it is the size of the block times the number of the block that you're in. So basically, x location will be your x plus how many threads are before you, right? So your index is basically thread index.x plus how many threads are before you, that would be your own block number dot x times the size of block dot x. So this will show you the actual physical x location. Same happens with y. So what is the y here then? Y is equal to your y plus how many threads are before you in y, right? So that will be your thread index.y plus your own block index.y times the dimension in y of each block. So your x and y is calculated easily. So x is thread index.x plus block index.x times block dim.x, and y is going to be thread index.y plus block index.y times block dimensions.y. And finally, in the actual calculation inside of your image, then the offset that you calculate is going to be x plus y times block dim dot x times grid dim dot x. How many blocks are, what is the size of these blocks, times your y plus your own x. And x and y we calculated them from here. So with this in mind, now let's go in and let's start writing our program. What we're going to do is we're going to calculate x and y and the offset for each thread. Then we're going to create a shared memory, and we're going to make the calculations in shared memory, and then store the results from shared memory in the global memory. And then we copy these results to show on the screen on the host. So now our code is going to be very simple. We're going to go up in the kernel, and in the kernel what we're going to do is we're going to create our x and y. So int x, as I said, is going to be thread index dot x plus how many threads are before you, which is going to be block index dot x times block dim dot x. Let's calculate y. Y is going to be thread index dot y plus block index dot y times block dim Now that we have calculated the x and y, let's actually calculate the offset. The offset of each pixel is going to be the new x we calculated plus the new y times blockdim.x times griddim.x. And this will be the offset location of each pixel in the data pointer that we have. So these are the simplest parts of this calculation. Now next, what I'm needing to do is to create a shared memory. Remember, I have a 16 by 16 block. I'm going to create a shared memory of that same size. So to perform a shared memory calculation, I'm going to use the shared keyword, and I'm going to call this, actually let's make this a float, and I'm going to call this shared, and it's going to be size k by k. Actually capital K. Now we're going to also create a constant float, and let's call this period, and let's make this for now 128 f. That would be how many pixels should be the parameter of each of the circles that I'm going to be creating. The next step is to perform the calculation of what would be the color of each pixel depending on the size of the circles that I'm going to create. So I'm going to do that and store it into the shared memory. So the shared memory of thread index.x, thread index.y, within each block, I'm going to calculate it according to this equation. 255 times sine of 2 times pi times x plus 1 times sine of 2 times pi times y plus 1 and the whole thing I'm going to divide it by 4.0 float. Write this a bit more neatly. So this is going to be my calculations. I'm going to calculate the 2 pi x, sine of 2 pi x plus 1, multiplied by sine of 2 pi x, 2 pi y plus 1, and then divide it by 4, and then multiply the results by 254. That would be the content, the color of each pixel, depending on the equation that I'm calculating here. The next step is to store these data in the global memory. Remember, my global memory is called DST, and so I'm going to write in at its offset times 3 plus 0. I'm going to write shared of thread index.x and thread index.y. Essentially, I'm going to copy the color value of or rather the value of the shared memory 3 times for red, green, and blue of my image. So I'm calculating the results in the shared memory, and then I store the shared memory values in the global memory. Now let's see if my code has any compile errors. Well, I don't have any compile errors. Let's run it. Oh, I found my problem. I need to divide this by a period, because otherwise I'm not going to get a reasonable value. And here it is. Alright, let's run this program. Okay, so here's what happens when we write the contents directly from the shared memory, thread x, thread index.x, and thread index.y of shared memory into the global memory. Each pixel is going to write its content directly into the global memory. Now, let's change this program a little bit and have each thread to basically write in the opposite location. So thread number 0 wants to write into location number 15, and thread number 15 wants to write into location number 0. So let's basically make our blocks kind of flip in that sense. So I'm going to add k minus 1 minus thread index to the locations in the shared memory from the global memory. So I'm basically performing a mirror operation here. Let's perform this calculation and let's see what happens. Voila! This is a problem. What happened here when we try to have the shared memory store the values, the contents of its values, into the global memory? The problem that you can see here happening is that I'm actually making each thread to calculate its location based off of this equation here. Then what I'm doing is I'm looking at somebody else's calculation from the shared memory and trying to write that data into the offset location of my main memory. The problem is that by the time my current thread number x, thread number y, is reading the content of shared memory location 15, 15, for example, for thread 0, 0, the thread number 15, 15 may not have finished its operation. Therefore, thread number 0 is going to read an invalid data from the shared memory. And so all these red, yellow artifacts, blue artifacts, cyan artifacts that you see here, the orange artifacts that you see here, are caused by the copying of a shared memory into the global memory before the thread responsible for that shared memory have had the chance to finish their calculation of this equation. So this should show you what exactly the problem was. The collision that happens is that some memory unit, some thread, is reading somebody else's data from shared memory to the global memory when that person has not finished their operation on the global memory. So that's one of the biggest problems with the shared memory. It is relatively faster than just directly working with global memory. The problem is that you need to make sure that the data that you're accessing is a valid data. How could we go about solving this problem of erroneous shared memory accesses? Here's the problem that was caused. Some thread is calculating something, but some other thread is reading the data from their shared memory before they had the chance to finish their operation. So the simplest way to solve this problem is a barrier. So what we're going to do is we're going to basically insert a sync threads barrier between our calculation into the shared memory and our readings of the shared memory. So what I'm doing is in each thread when they're calculating, I make sure that all of the threads finish this line before any thread will be allowed to read from the shared memory. So you see that what I'm going to do in this case is I'm going to separate my writes accesses into the shared memory and read accesses from the shared memory. I split this. I spread these operations and that would solve my problem. So if you run this program, then you would see that your operation works normally, and you should not get those ugly looking artifacts. So of course what's going to happen, what is happening in this case is that each of these units, each of these squares that you see where the dark lines are in this image belongs to a block. Okay. Then within each block I have a thread index and a x and a thread index dot y. What I'm doing is I'm calculating the operations there, and then I'll have this thread write into this other point pixel, and for example this thread to write into that pixel. So basically I'm kind of mirroring the calculations of my reads and writes, and that gives me this kind of nice looking pattern of kind of blocky looking circles that I created. Now notice by period, basically I'm basically dictating the size of these blocks. So if I have a period of 128, then I'm going to effectively have 6 periods in my 512 by 512, rather 4 periods of 512 by 512 in my image. So if you decrease the period, for example, make it a 64, then you're going to have more repetitions. Let's see what happened with my program. Yeah, it probably didn't close. There you go. So if you decrease the period here, you're going to see that you're going to have more of a repetition in your operation. So a 32.0 F is going to create even more patterns, as you see in here, and of course your sync thread is what is effectively keeping your erroneous memory accesses. So if I remove the sync threads, as you see, some threads will not finish before I'm reading from the contents of the shared memory to store into the global memory. So let's place back shared memory in. And then smaller periods. I'm going to create more fine-looking spheres, patterns of spheres for me, and larger periods, for example, something like 256. It's going to be a very, very rough calculation, rather a very rough allocation of my pixel color values. Okay, so this is an example of buffering your data. Now next I'm going to show you how you can perform a time calculation with CUDA events. Alright, in CUDA, in order to calculate the time that it takes for your kernels to operate, we can invoke CUDA events. There are two special kinds of events that we can use, or rather functions that we can use. CUDA event create, which basically stores the CPU, or rather your GPU clock time on your onto a CUDA event variable, and then CUDA event elapsed time that takes two CUDA event variables. and then calculate the differences in time in terms of milliseconds for those two events that happened, and stores them into a floating point number. Now I'm going to use the CUDA events in my helper function. So I'm going to create two CUDA event underscore t variables, just like the CUDA error we create. I create a CUDA event called start and stop. Then I can use these start and stop in conjunction with CUDA create, and then when I'm basically calling up a function, I can start recording into these two events. So let's use my CUDA status error code to check for the error in CUDA event create function. Then I'm going to call CUDA event create, and I'm going to pass to this the reference to my start of the CUDA event. What happens is that the pointer for my CUDA event is going to be created at this point. Then let's just catch the error. CUDA status. If it's not equal to CUDA success, then I'm going to print on the screen CUDA event create failed. Go to error. Then I'm going to replicate this code for the stop event. CUDA event create the reference for my stop. Now I have these two variables start and stop that I can use to record events on my CUDA. Now also let's create a floating point, call it elapsed time, or time spent. Wonderful. Now that I have these variables, I can basically go ahead and record times into these variables. So before I invoke my kernel, I'm going to start recording into the start event. I invoke my kernel, then I record into the stop event. Then I synchronize the stop, and then I will calculate the elapsed time. Okay, so let's start recording. CUDA event record into start, invoke the kernel, and then record into stop. Then synchronize the stop event, and then calculate the time that was elapsed. So that operation calls the function CUDA event elapsed time. In this, I'm going to pass the reference for my floating variable, called it time spent, and then the start event and the stop event. And this function is going to be calculate. It's going to calculate the time that was spent from between the two events, the start and the end. And as you notice here, or start and stop. And as you notice here, the only operation that I'm performing between the start and the stop time is the invocation of my kernel. Effectively, the time spent is going to be equal to the amount of time that it took for the kernel to calculate. And then I can write this on screen. And so what I'm going to write on the screen is that time spent on CUDA shared memory with synchronization with sync threads equals %32f, and the time spent variable. Now if I run this program, it'll tell me exactly how long it took for this event, or rather for my kernel to operate. And it took about 0. Okay, yeah, let's put a 0.32 f\n. It was 0.51 millisecond. I'm just going to format my calculation here. Okay. So time spent on CUDA shared memory with sync threads 0.5 milliseconds. Now let me just decrease this 128 to something like 32 and see if that has anything to do with changing the time. That had nothing to do with changing the time as you expected, because basically I'm using the number of threads and the number of blocks, 16 by 16 threads in each block, and 512 is going to be the size of my my grid, or my image, the image that I'm creating. So let's see what happens if we remove the sync threads. So if we remove the sync threads, actually let me just change the text, and let's go ahead and remove the sync thread. Well, oddly enough, with the removal of my sync threads, I didn't really make much of a difference in this image calculation. And the differences may be fairly small in the small size of shared memory anyway. So for a 1024 by 1024, we've got 1.98 milliseconds for the calculation without the sync threads. Then with sync threads, I'm going to probably get roughly the same speed, maybe just a little bit slower. As you see, it was just a little bit slower, so it's 2.01 millisecond, about 0.03 milliseconds difference when I added shared, or rather sync threads here. Let's make this 496. And I'm running with the sync threads. So now I have a lot more threads that need to be synced. 31.9 milliseconds with sync threads. So I'm thinking if I remove the sync threads, I'm gonna be a little bit faster. .57. So I took about a half a millisecond. So a sync thread actually added half a millisecond, or rather, yeah, half a millisecond time to this huge data. pretty much half a millisecond difference with this huge data size that I have here. So this is basically so I effectively created a really huge image, 8,192 by 8,192 with sync thread. It took me 125.8 milliseconds. 125.8 milliseconds with sync thread added. And if you remove the sync threads, you change from 125.8 millisecond to 114.07 milliseconds. So that is practically about 11 milliseconds for this huge data. But the cost of it is wrong, erroneous calculation. So this is it for your lab of communication patterns utilizing shared memory and communications between your threads, and how you can work with your shared memory to pass data between threads. Effectively, in my case, my thread calculates a number and passes it to somebody else's global memory location. And to make sure that your data calculation is safe and sound, between each read access and write access from and to your shared memory, you would have to pass or present or create a barrel synchronization, and that means a sync threads operation between each read access into shared memory and write accesses from shared memory, and vice versa. So I hope this lecture was and the lab and then the accompanying lab was useful. And basically, from this point on, you should start working on your project 2, which basically utilizes an image and blurs it, and you need to use shared memory, just as you see here, to load data from global image into your shared memory for blocks, perform the operations in each block, and store the data. And hopefully that will be a beneficial and an interesting project for you all to work with. With this, I'll let you go studying some more, and I will talk to you for Unit 8. Thank you very much.